On October 29th, something skimming the sun blinked in a way no comet ever had. Astronomers expected a predictable brightening. Instead, the light jumped. Bright, dim, bright again, in a precise rhythm that didn't fit any model. Instruments from Chile to Hawaii recorded the same pulse, and the timing was too exact to be noise. What looked like a tiny wobble at first suddenly read like a signal, and that small, stubborn mismatch forced scientists to recheck everything they thought they knew about interstellar visitors. But that pulse was only the beginning, and what followed would make the routine idea of a comet start to feel dangerously inadequate. At first it looked like a simple data glitch, a brief flicker in the light coming off 3i Atlas as it swung around the sun. But the pattern repeated. 3 sharp spikes of brightness, each separated by exactly 58 minutes. Not random, not chaotic, but rhythmic, like a heartbeat echoing across space. The European Space Agency, NASA's Jet Propulsion Laboratory, even a few amateur observatories all caught it. Different instruments, different continents, same rhythm. Comets don't do that. They flare once when ice boils off, then fade away in a messy cloud of gas and dust. But Atlas's light pulsed 3 times, each surge identical in strength, each drop just as clean. At first, scientists blamed interference, maybe solar radiation flooding the sensors, maybe a calibration error. Yet when the same pulse appeared in independent data, the excuses began to crumble. What really startled researchers wasn't just the timing, it was the precision. Each pulse arrived within seconds of the predicted interval. Nature rarely works on that kind of schedule. It almost looked deliberate, as if something on the object's surface was modulating sunlight, flashing on and off like a slow beacon. For a moment the idea seemed absurd, but then a deeper mystery surfaced. During the pulse sequence, Atlas's rotation appeared to change. Just slightly, but measurably. Its spin shortened by 14 seconds. That's an impossibly fine adjustment for a tumbling rock travelling at tens of kilometres per second. Something about that connection between light and motion didn't fit natural physics. Astronomers argued over every possibility. Outgassing jets, uneven melting, even magnetic interference from the sun. Yet none of them could explain why every observatory on Earth saw the same pattern at the same exact moment. A signal, a mechanical rotation, a coincidence written in light. No one knew. But whatever caused those pulses, they were the first hint that 3i Atlas wasn't just reflecting sunlight, it was responding to it. And as the object moved closer to the sun, that rhythm would only grow stranger. Because if the light was puzzling, what happened to the heat made even less sense. When 3i Atlas neared the sun, astronomers thought at least one thing would behave normally: the heat. Every comet follows the same script. As it approaches the sun, it warms steadily, peaks at closest approach, and then cools off. Simple thermodynamics. But 3i Atlas didn't read the script. Its temperature graph looked like static. Rising, crashing, rising again, and disturbingly, those spikes matched the same 58-minute rhythm as its light pulses. Objects made of ice and rock don't heat and cool in seconds. They store energy, release it slowly, and drift through predictable curves. Yet here, one side of Atlas seemed to chill while the other suddenly blazed hotter, as if something were moving heat through it on purpose. NASA's Parker Solar Probe and the European Solar Orbiter both logged the same pattern, confirming it wasn't an instrument glitch. For a few minutes during perihelion, Atlas radiated more energy than it received, an impossible act without some kind of internal system managing it. Even stranger, sensors caught brief flashes of infrared light around 850 nanometers, wavelengths that match heated metal, not vaporizing ice. Spectrographs hinted at nickel and cobalt, materials that shouldn't survive that close to the sun, at least not on a fragile comet. Some researchers quietly suggested contamination from the spacecraft sensors. Others weren't so sure. To make matters worse, the heat didn't come from the side facing the sun. It bloomed from the shadowed hemisphere, the dark side, glowing faintly where no sunlight touched it. That meant either the object was trapping and redirecting energy internally, or something beneath the surface was generating its own heat. A memo from the Jet Propulsion Laboratory called it thermal phase inversion, a sterile phrase for we don't know why it's hotter in the dark. By now, scientists had stopped calling the event a comet flare. They'd started calling it an anomaly. The temperature pulses, the metal-like emissions, the synchronized light. It was too much coincidence for comfort. And if heat could act like that, maybe the surface wasn't made of dust and ice at all. Because when the cameras zoomed in next, what they found streaking from the object didn't look random. It looked structured, and it pointed straight towards something no one was prepared to admit. When the first high-resolution images arrived, everyone expected chaos. A blur of vapour and dust erupting unevenly from the surface, the usual mess of a comet under solar stress. But 3i Atlas didn't erupt. It aimed. Instead of random sprays, 3 distinct jets shot out in perfect formation, each emerging from precise coordinates on the object's surface. Their geometry formed a near-perfect triangle, symmetrical, stable, and repeating. To the untrained eye, it looked engineered, not accidental. The jets fired in intervals synchronized with the same rhythm seen in the light and heat data. It was as if the entire body was running on a timer. Normally jets destabilize a comet's spin. They make it wobble or even break apart. But Atlas stayed steady, its rotation consistent, its motion smooth. In fact, the data showed it sped up slightly after each burst, as though the jets were gently propelling it forward. Analysts at the European Space Operations Centre noticed that the object's angular momentum increased, not decreased, during these emissions. One researcher put it simply, if this is natural, it's the neatest accident in the solar system. Spectrographic readings made things even stranger. Each jet carried a different chemical signature, one rich in carbon monoxide, another in molecular oxygen, and the third spiking with traces of nickel vapor. Nickel doesn't just drift off ice. It vaporizes at over 1,000 degrees. Whatever was coming out of Atlas wasn't ordinary gas, it was metallic, dense and magnetically active. The Parker Solar Probe's magnetometers caught faint ripples, magnetic fluctuations that pulsed in perfect harmony with each jet. The pattern looked nothing like random solar interference. It looked coherent. Some scientists described it as controlled plasma interference, while others, less cautious, called it what it seemed to be, thrust. That idea didn't sit well in official reports. Comets don't steer themselves, and suggesting otherwise risked ridicule. But as the object's path began to shift, not randomly, but with purpose, disbelief started to crumble. Over several hours, Atlas's velocity vector nudged just slightly off its predicted track, aligning perfectly with the direction of the jets. It was subtle, less than a meter per second, but enough to raise the impossible question. If those jets were propulsion, then 3i Atlas wasn't drifting. It was maneuvering, and that's when the clock started to go wrong. Because whatever this thing was, it wasn't just bending light or heat anymore, it was bending time. When 3i Atlas reached its closest point to the Sun, astronomers expected the data to flood in perfectly synchronized, every telescope and probe recording the same moment from slightly different angles. Instead, time itself seemed to split. NASA's Jet Propulsion Laboratory marked the Perihelion event at 14:28:36 UTC, but ESA's solar orbiter logged it 3 minutes later, and Japan's Hinode probe even later still. That shouldn't happen. Their atomic clocks are matched to the millisecond, verified across the deep space network. At first, analysts blamed transmission lag, but the timestamps were embedded in the raw signals. These weren't network errors. Each observatory genuinely recorded a different moment. The discrepancy grew worse the longer the object was tracked. It was as if 3i Atlas existed in slightly different timeframes depending on who was looking. Then came the blackout. For nearly 2 hours, every telescope, probe, and ground-based observatory lost visual contact. The object just vanished. Not dimmed, not hidden behind solar glare, but gone. When it reappeared, its spectrum had changed, its brightness subdued, its surface matte instead of reflective. And buried deep in the data, one detail refused to go away. During those 2 missing hours, Parker Solar Probe detected a sharp inversion in the local magnetic field. For 3 minutes, the magnetic polarity flipped, then normalized. That doesn't happen in isolation. It's the kind of signature you'd expect from a collapsing electromagnetic field, something turning off and then back on. When the object returned, it was slightly off course, its velocity lower, and its spectral fingerprints subtly different. Whatever happened during that blackout, it wasn't passive. Agencies called it a data dropout. But among scientists, one question started to spread quietly. What if that blackout wasn't an error? What if it was a shutdown? Because as soon as Atlas reappeared, something else started repeating. A bright metallic signal that pulsed with unnerving precision. And that pattern would unlock the next clue in the mystery. It started as a faint shimmer in the ultraviolet range, a line at 341.4 nanometers, small enough to miss unless you knew what to look for. It was the spectral fingerprint of nickel, a metal that should have burned away long before the object ever reached perihelion. But this wasn't random trace metal. The ratio of nickel to other elements stayed perfectly constant across hours of observation, exactly 100 to 1, identical to refined industrial alloys used in heat shielding and aerospace engineering. Natural chemistry doesn't hold ratios that steady. Even more suspicious, the nickel emissions weren't continuous. They came in bursts, short, precise, rhythmic. Every time the nickel line flared, 3I Atlas's velocity shifted ever so slightly. University analysts in Bern ran the numbers and found a near-perfect 0.96 correlation between those flares and the object's micro-accelerations. Nickel, in vaporized form, can react under magnetic fields to produce thrust, the same principle behind experimental plasma engines, and this thing was doing it in deep space, at the exact rhythm of its earlier light and heat pulses. By now, nobody could agree on what to call it. NASA used terms like directed energy redistribution. ESA called it structured outgassing modulation. But stripped of the jargon, it meant one thing: control. Atlas wasn't just venting gas into space, it was channeling it, using it. And that control didn't stop at heat or light. Soon, its very course began to change in a way that couldn't be dismissed as coincidence. By late October 31st, tracking data from multiple observatories revealed a subtle but consistent curve. Instead of shooting out into deep space, 3I Atlas was adjusting its trajectory, flattening its path until it lined up with the ecliptic plane, the same invisible sheet where Earth and the other planets orbit. Interstellar objects like Oumuamua cut through that plane at steep angles and vanish forever. Atlas, however, was leveling itself with it, steering into the solar system's highway. Each day the adjustment grew more precise. The object was now applying gentle, sustained acceleration exactly parallel to its orbital path, not perpendicular. In other words, it wasn't falling anymore, it was cruising. When analysts overlaid the object's magnetic and velocity data, they noticed the same 52-minute rhythm, the same pulse that started it all. Each flare of nickel, each magnetic surge, matched another tiny lateral push, slowly reshaping its orbit into perfect alignment with the ecliptic. Inside the European Space Agency, a restricted briefing quietly circulated. Its conclusion read like science fiction. Observed course correction exhibits coherent acceleration phase, matching rotational modulation cycle. No known natural mechanism reproduces this behavior. Translation? It was steering itself on purpose. By November the 1st, the path was clear. 3I Atlas wasn't drifting out of the solar system like an ordinary comet. It was settling in, sliding neatly into a lane shared by the planets. And once scientists realized where it was heading, silence swept through every lab that still had eyes on it. Because if the data was right, its path would cross ours. And that left only one question. What could possibly want to come this close? Even now, telescopes still track it, a fading dot gliding along the same plane as Earth, quiet, steady, unchanging. The official line calls it a highly unusual interstellar comet, but no one really believes that anymore. The light pulses, The heat inversions, the nickel emissions, the blackout, the deliberate turn, stacked together, they don't describe a comet. They describe a system, something built to survive, to adapt, to hide. For decades, scientists believed every object that passed through our solar system was blind debris, leftovers from distant stars just drifting through. But 3i Atlas didn't drift. It corrected. It stabilized. It learned. And then, when the sun's glare began to fade, it slowed down, as if deciding to stay. Some researchers whisper that it's still out there, following the ecliptic like a shadow, its signals faint but rhythmic, waiting for something, or maybe someone. Others argue that nature is capable of more order than we think, that chaos itself can mimic design. Maybe they're right. Maybe 3i Atlas was the universe's most convincing illusion. But if it wasn't, then something out there crossed light years of emptiness, arrived at our star and chose to linger in our path, not to announce itself, not to invade, just to watch. And maybe that's the strangest part. No signal, no message, just precision. Quiet, patient, deliberate. Like an eye blinking once in 1,000 years, then staring back in silence. Because in the end, 3i Atlas didn't prove that we're not alone. It proved something far harder to grasp, that the universe might already know we're here.